All right. Welcome, folks. Welcome back to the stream. How you doing? My name's Agent Ultra, and I'm here to learn about wave function collapse. It's a procedural generation algorithm used for generating textures and stuff. People may could also use it for generating poetry, whole worlds, and video games, things like that. On this stream, I mainly do stuff in Haskell. So if you're new to Haskell, welcome. Hi, if you're new to the stream, thanks for tuning in. And yeah, we're gonna get started here. So I'm gonna pull up my editor, jump right back in. So for the last few weeks, we've been working on the pre-processing step of it. So taking an input image and just generating some setup data we need to get the core of the algorithm going. And we're pretty much finished all the little pieces of that. I think we might want to tie it together into kind of like a top level function, but yeah. I think we're going to be able to get into the core of the algorithm this week, maybe. Probably. Alright, so basically the idea is that our user is going to take whatever input data bitmap they have, whatever pixel data format it has, and they're going to create a texture with it. So our texture is just a wrapper around that array of whatever value it is. We don't really know how the pixel data is stored. Is it word 8 or floats or whatever? Who knows? We don't really need to know all that much for the algorithm, it seems. So they create the texture, and out of the texture we generate a bunch of patterns. Patterns are like little subsections of the input texture. And we wrap around, we treat the texture as like a toroid, and we wrap around and we cover all of the overlapping patterns by taking that subtexture kind of size there and moving it over 1 pixel at a time, taking a new stamp, creating a new pattern with that, moving it over 1 pixel at a time, taking a new pattern with that, so on and so forth, all the way around. So we get a bunch of overlapping patterns. And for like a 10 by 10 input texture, the input textures are pretty small. With these patterns, we say like a 3 by 3 pattern, we should get about 100 patterns out of that. And then there's the opportunity there to also do like some rotations and symmetries with the patterns in order to generate interesting new textures. But for the most part, we're just really focusing on the patterns here and getting those. Okay, so that's the algorithm there to generate all the patterns out of the texture. And from that, we can bring up a new browser window. No, don't want that. Patterns, right? Generate all those. And then we need a couple little helper functions like overlapping. We need to know if a pattern overlaps with another. There's our little symmetry thing, which we can use if we want to tie things together. I don't know, function there. We also need to create a frequency hint map. So the frequency hint map basically allows us to know how many times in the input set a particular pattern shows up. So that's what this does. And then we generate the adjacency rules. So wave function collapse is basically like a forward propagation solving algorithm. We'll think like Sudoku. We start with an input grid. And there's a lot of possibilities in each cell of the input grid of like values that we could put there. In the case of Sudoku, it's going to be a bunch of numbers from 1 to 9. And by picking a number for a cell, we collapse it down and we propagate out that choice. So we eliminate that possibility, the possibility of, say we pick 3, right? So all the neighboring cells in that kind of corner of the grid, we eliminate 3 from all of those, and then we eliminate 3 in all the row that we chose for the cell in, and then all the column, all the 3s in the column. We remove the possibility of 3 from all of those. All right, so we propagate those out, and then eventually we should end up with a solved Sudoku grid, or at least in our case, a finished texture. So those adjacency rules are generated from our input data set. They just are, it's based on the overlapping of the tiles. All right, so our overlap function from earlier, if the pattern A overlaps with pattern B, then we allow it in our input our adjacency map, and we say, yep, that can be, those two tiles can be overlapping. And this map just lets us to, has a quick way of us just doing that, kind of pre-checking all of those. So when we're running the algorithm proper, it's just an index lookup. Cool. Last thing we needed to generate was just the color map. So because of the way the algorithm works, we're actually only going to be, when we generate the output texture, we only need to pick the top left corner of our pattern in order to fill in the pixel of the output map that we're gonna generate. And yeah, and once we have the color map, that's pretty much it. So we're gonna get working on, there's gonna be like 3 main components to the overall core of the algorithm. Kind of a high level sketch is that while we have, for some output grid, initialized output, for some initialized output grid, while there are empty, while there are uncollapsed cells, we're going to choose a cell with the lowest entropy. Now, once we've chosen that cell, we collapse it. That means picking a tile from, or a pattern from the possible patterns. Then we got to propagate that choice. Or across the wave. And you might hear. Sounds cooler. And that's kind of where the name of the function gets its, or the name of the algorithm. That's where this algorithm gets its name from, I should say. The wave function collapse, right? The wave is the grid of cells, right? And this propagation step, right, it takes your function and propagates out the results of that function across the wave, right? Collapsing it down to a single value or a single grid of picked tiles. Now, there are some caveats to this that I think we'll encounter perhaps later, and we might want to figure out how. I haven't really figured out which way I want to solve it yet. There's no one right way to do it, but as you can imagine in Sudoku, picking a particular number, if you had a completely empty grid, right, with no pre-picked numbers, like you pre-collapsed cells, like you do normally in the newspaper version of the puzzle, right? You can imagine if a completely empty one, you started with that and you just picked, say, 5 for one number, just started going from there. And then you propagate out, you eliminate all the 5s, and then you pick another one, and you pick a value for the next cell, and then eliminate and propagate out all of that. That you could come to a point where you get what's called a contradiction. Contradiction is when you pick a cell that has no possible patterns in it to collapse to. And so through the propagation step, all the possibilities for this cell have been eliminated already. When you go to look at it, and you're like, oh, I can't collapse it to anything. It's got the empty list. It can't possibly be any other tile. This has already been eliminated. In that case, there's some different ways you can handle it. You can either, like, some algorithms maybe will take this approach. The easy way out is to just start over, make some different choices, and try again. You know, and then maybe like have a overall controlling function that kind of just keeps track of how many times you've retried, and then might throw an error if you've run out of attempts or something. Other approaches to this sort of like implement backtracking. All right, so in that case, you undo some of the choices, prior choices you made. So you undo the propagation, and you undo that choice, and you take a step back, and you try a different choice, and then you propagate that out, and hopefully you don't reach a contradiction again. A little bit more expensive in terms of generation, right? But you get, while it's fairly rare to get a contradiction, perhaps, I guess we'll see in practice, you're more likely to get a successful outcome with backtracking. So the give up and start again approach, or backtracking. Maybe others. Don't know. So that's pretty much it there, you know? We're gonna start though, I think, with defining what a cell is and kind of defining the data structures, the types here. So let's define the cell. The cell has possible values. Possible patterns. Possibilities. That could be... this is going to be like... we're only going to talk while we're doing the algorithm. We're going to only talk about the pattern indexes. So this could be a list of booleans, and this list would have to have the same indices. The index of each element in this list would correspond to the tile or the pattern index. Lists are super inefficient though, but they're good because we can console. We're going to be mainly eliminating from this. No, it's going to be a fixed size, really. Actually, it's going to be true or false, so it could be an array. Just a flat array. Of booleans. Right. So for our index map, we have like 10 patterns. This will be an array of length 10, and we can initialize all of those to true. So let's create a little initialize function, Excel. That's going to be a cell. It's going to take... We have to initialize the size of the array. We're going to need maybe an integer. And so that's about it. We know we're going to initialize the Boolean value too, so. So it's going to be cell. Array dot list array of size. Or not clear from reading the code what size means here. It's really supposed to be the maximum index, I guess, of the tile indices or the pattern indices, which is just an int. I'll call this max index. And this should be max index. And then we need the list. And that's going to be false, or constant value, or from 0 up to max index. Oh, the bounds are here. Right, we don't have to do that in the list. We have to do that here, so... And this could just be repeat false. If we want to make a cell, so we have 10 pattern indices. We have to derive show for that, of course. Reload that. Yeah, it's not gonna, I don't like that necessarily. You could just give us the list of pattern A's. We'll actually ignore the A's and just take the indices of that. We'll just take the length patterns. Which seem... yeah, seems way too... Let's just do int there. Yeah, you know what? Max pattern index. I'm gonna go with that. I think that'll probably make sense. Like, if I do make cell 10, that means I've got 10 patterns. Well, no, the length of the patterns wouldn't be the max pattern index, right? It would be 9 is what we're looking for if we had a list of patterns of length 10. So we'd have to get that from something. Maybe we could have a function for it. It's the output of this function here. We get this list, and that's kind of what we compute a lot of the other stuff from. Like frequency hints takes that list pattern A, and I think the color map as well. Adjacency rules does as well, and the color map generation stuff does as well. Yeah. So we could wrap that up in a new type to make it a little bit more clear what it's doing. Or we could put some functions in. Like if we change this, because that way, I just want to make it clear that when you're making a cell, what index to get to pass in here. Maybe this will be kind of like an internal thing. Maybe, I don't know. But we have no real way of getting the pattern index numbers out. We just use pattern index as a type alias in the color map. as an argument for an internal function in the adjacency rules, in allowed. So, in all these kind of other places. But it's not clear where that's coming from. So why don't we try that approach? New type, pattern, resolve, patterns, texture patterns. Pattern result? I don't know, something like that maybe. Of A. Yeah. Yeah, actually, let's make it a structure. Patterns. That can be our list of patterns of A. Then we can have pattern max index. Kind of pre-computed. And just find those there. Alright, so then we already have a function, pattern max index, from our pattern result to get that, to pass into make cell. Alright, so we can even pass that in instead. Here. And then we don't need necessarily max index here. Use overloaded records to destructure that pattern result structure. And pattern result max index. Needs to be a value here. Let's pull this over to the left. And what did I call it? Pattern max index. Oops. I want to call this all max index just to be consistent. There we go. Bueno. Super. Wonderful. Okay, so we pull that in like that. Then we can go Excel and our pattern results, whatever. We're going to use this mark constructor, but if I have a pattern result saying 9 as my max index, then we will get the correct cell generated based off of that. Okay, so to get a pattern result, you can get it from patterns. Pattern result of A. And all we have to do pattern result here. No, we're gonna need to let bind this. Patterns. And put the constructor here. So we're going to take patterns, and then we're just going to compute the length of patterns minus 1. And then here, I'll just call it keys. Okay, I think that's good. Oh. That. Oh, keys. There we go. That's better. Okay, so now that we can extract that from patterns, we get the pattern result out. We could use pattern result with all the other pre-gen stuff if we wanted to. We do fold L here, the adding the pattern element, to color map. Yeah, this is all still okay. Although we might as well just go ahead and use it. Oh, this is really nice. I don't think we'll be exporting these necessarily in our public API in the end anyway, so let's just leave those because it's just kind of nice having it there that way, because we can still get the patterns out from the pattern result to pass into those functions, so that might be fine. Okay, so making cell. Now we know we can get that pattern result max index just fine. On the pattern result, we don't have to do any quirky calculations and making sure that the user inputs the right number and all that sort of stuff. I like that. That's better. It's kind of API I like to work with. Okay, so now that we have a cell with all the cell possibilities, we need to make our output grid. That's going to be like our wave. The thing that has all of the cells with all of the, where initially all of the cells have all the possible patterns. That grid is going to be of a fixed size, where it's going to be a bunch of cells. It's this. Right, and the cells are going to be arrays of bools, maybe some extra data in them. But for now, just arrays of bools. So it's almost like going to be an array of arrays. But the grid size isn't going to change. Neither is the array size, so I think there should be fine to be an array as well. But we're going to create a type for it. I'm going to call it gridded. Do we need anything else on that? No, maybe not. Function gets cells. It's going to be an array It's going to be two dimensions. This would be an array tuple int. And cell. As always, we'll just derive a couple of basic classes that we like to derive to make things easy to debug and use. Good. Okay, so we got the grid. And now we need to instantiate the grid and the size that we want. I don't think the output has to be square. Don't quote me on that, but I'm pretty sure it doesn't. Pretty sure we could have a wide rectangle if we wanted to. I think most of these are squarish. But yeah, I think we could generate wide. So if we can give independent dimensions for the length and width, or width and height, maybe. Yeah. Let's do that. I'm using int here and int here. I know. Negative sizes don't make sense. I know. I'm going back on some things, maybe. I don't know. Let's just roll with it for now, though. Okay. Because normal up here, say in pattern, right? Pattern size is a word. A word is pretty much an unsigned integer in Haskell. Right. And the reason for that is so that we can just completely ignore negative values. We don't have to consider them. But the reason why I'm a little bit on it is because as we've been developing this and working on this, we have quite a bit of coercing to do to enum from integral to go between things that require integers and other things, and then going from integers back to the word. All right, what even is 2 enum of -1? Right, exception. Bad argument. Enum A. Right, so we're going to set type applications. Yeah, so you get a runtime exception, which is no good. Right, so you always want 1, or positive numbers for that. And really, pattern size should be a positive integer. It's true. Negative ones don't make sense. But are we going to export pattern in our algorithm to our users of this library? That I'm not so sure. So if we don't, right, we can validate our numbers against we could take just plain old integers and validate that they're integers and that they're the right numbers in our like public API. That gets kind of messy too, though, you know? So what do you return for the failure case? So I don't know. I'm kind of wishy-washy on it. Maybe these should be words. Because the idea I was going for, at least when I started doing this, was like, let's try this idea of using types that, you know, prevent the caller from giving us bad data. Let's try and keep going with that for now. We'll do a retrospective maybe on it later. My midpoint retrospective is, maybe we can just use integer and just throw an error somewhere if you give us bad arguments. Okay, so making grid, we have the width and the height. List array. And we have to give the bounds here, so we're going to go from 0, 0. Up to, I think including width and height, if I'm not mistaken. And then we're going to give well, we need the pattern result as well. Yeah, we're going to need the pattern result of Haskell. In order to make all the cells. And then we got to wrap that up in our grid constructor. And of course, this is what I'm talking about here. Yeah. Okie dokie. Oh, actually, Muxile should be true. Be true. In the beginning, all possibilities are possible. All patterns may be represented in any given cell. Or as possible values for the cell. And as the algorithm proceeds, we'll eliminate possibilities. Collapse cells. Okay, speaking of which, we should probably have functions for that work on those cells. Collapsing one and eliminating would be the other ones. And then we also need an entropy function for choosing cells. So, and we also need to know if a cell is collapsed or not. right, while there are uncollapsed cells. So that means we need to know if the cell is collapsed. And let's see. Okay, so what does it mean for a cell to be collapsed? It means we've picked one pattern to be the value for that cell. All right, so as you update the grid and we propagate things out, we're going to be picking one to collapse. All right, and if we want to know if the cell is collapsed, there's only one true value in the array. Or we could set a value in the cell. And that could be, actually, maybe pattern index. Or maybe to make this more clear. Right, so we have the array of all possible cell possibilities. And then this function becomes trivial for collapsed. For some cell. If the cell.cell is just cell collapsed. That's true. Otherwise, it is false. Yeah, I think in this case I'm actually just going to use the field names here. Ah. There we go. Okay, yeah. Pull it over a little more than that. There we go. All right. Yeah, so we start off with all possibilities. The cell's not collapsed. Now, if we want to collapse a cell, we need a way to pick one. Because we basically are supposed to, like, kind of just choose a value. So we need some kind of randomness. in order to do that. Actually, we should probably checkpoint here. Create commit. That's a good point. Let's go there. Mirror. Mirror. Add cells and grid. I'm gonna hold off on doing collapsing just yet. The other function we need on cells after collapsed, so we know how to get uncollapsed cells, is this step here on line 213. We need to choose a cell with the lowest entropy. So we need an entropy function for calculating the entropy of a cell. This is kind of a keystone part of the algorithm as I understand it, and we should probably go to grid bugs just to get a hint as to why that is. This is also explained in the main wave function collapse algorithm as well. But it goes into some pretty good details here. Way more detail, I think, than the main GitHub repo for wave function collapse. Anyhoozle, there's a lot of math. It's some math. However, it's not too bad. We're just talking about probability distributions here. The reason why we want to calculate this stuff and figure it out and do this mathy thing is so that we can pick a cell to collapse that is going to have the highest likelihood of being adjacent to our input tile, I believe. I think. Maybe I'm wrong on this one. You don't want to choose completely randomly, which is I guess if we were to like choose completely randomly, right, of all the possible cells that we could pick, we just pick one and collapse it. Just, blah. There it is. Yeah, there's the line. The intuition behind this is to lock in one of the cells with the least uncertainty. Yeah, that's kind of right. So that means like when we pick the next cell we want to collapse, it is going to have the highest likelihood of being adjacent or being overlapping with the pattern we just picked. If that makes sense. So if you can imagine like the stacks and all the cells are all like stacks of all the patterns that we have. So each cell is, say, 10 patterns we have, right? So each cell initially has 10, right? And we collapse one, we pick one, right? Now all the neighboring stacks are still 10 high, but we're going to do the propagate step now, which means we're going to use our adjacency rules to eliminate all the patterns that can't be in the possibilities of the adjacent cells, right? And so we might get a stack of like 5 and like a stack of 3 in one corner, a stack of 2 in the south, so on and so forth from this grid. It kind of like creates a little divot in our hypothetical imaginary table, right? And if we were to just choose randomly the next cell to collapse, So even from the neighbors, right? We get like a very noisy output and probably a very high probability that our wave won't collapse all the way, and we'd have to like retry a lot. So instead, by choosing entropy, we're picking basically the smallest stack of the ones that are still on the table. So like maybe the one that just has 3 in it. Right. Now, there's the possibility you can run into where like you have a stack of 3 and a stack of 3, and which one has the lowest entropy. Well, you could just choose randomly between those as well. That would be fine, but because it amounts kind of the same thing. They both have relatively the same amount of uncertainty, as this intuition says. So yeah, that's kind of the gist of it. This gives you a more formal introduction in how to calculate this. It looks kind of scary. It's not that bad. Okay. P of x, that's just a function. We use those in Haskell all the time. Right. We have an unknown value with n possibilities, right? That's our pattern. Right. And this n x1, x2 to xn is our stack of patterns. The probability of a given value, a given pattern, represented as a number between 0 and 1, is expressed as this function. Okay. So whatever, it doesn't matter a whole lot what this function is, but it's going to return a value between 0 and 1. And then the entropy of your unknown value is this formula here. Okay, so we're just going to subtract together a bunch of multiplications from each other. Okay. So this log function here, they say, is arbitrary. So you can use whatever log you want. And this is y. So calculating all of that out using computer code can be simplified. So they're doing just some transformations here, I guess, on the formula. And then we got an implementation here. So relative tile frequency. So the simplified entropy definition is relevant to choosing the next cell as a frequency hint. That's what we generated in the pre-processing steps, is effectively a discrete probability distribution of possible choices of the tile. So that's like how often that particular tile shows up in the tiles and all the tile sets, like the whole thing. So that frequency is like the number of times it shows up. It's discrete. It's like one value. So, or sort of tile pattern, you know. So we already have this, I think, in the map, if I'm not mistaken. And then we need a function. Well, they use a function here to add up the relative frequencies of all possible tiles. This corresponds to the total weight in the simplified entropy equation. All right. Okay. So total possible tile frequencies, let's do that then. Total possible tile frequency. Probably going to take our tile frequency map. Cell, probably a cell. And returns U size. I think that's an integer. Summing from this relative frequency function, which also returns a U size. The tile index. So I think that's just reaching into the tile frequency map there, taking out a number and adding it, summing. That's what it does, right? So some integer. Oh yeah, I got my error messages showing up again in Emacs. I just had to update a bunch of packages. I was just being lazy and hadn't done that in a while. Tile frequency, I didn't call it that. I called it like frequency map or something. Did I not create a type for that at all? Let's see. What did I do? Frequency. Oh, I just returned a map and didn't. Let's go and create a new type for that. Frequency hints. And that's going to be frequency hints. And that's going to be our map int. And we'll add our usual boxes there. Really, that's not going to be int. That's going to be pattern index, which is int, but just for readability's sake. And then we can have a little function there for getting things out of the frequency hints for a tile index, right? Just index it to a simple indexing function. Let's call it frequency. Pattern index to int. Oh, and we're gonna have to give the frequency hints as well. We'll give it in this position. Frequency. Yeah, frequency hints. And then we just have to, well, because it's a map, it might return an int. If that pattern index is in there. In this case, it'll just be lookup. X. Okay, and this can return that now. And we just wrap up our function here in our constructor. I think that all goes. Let's get our builder going too with the tests just cause. I usually start the stream that way, but hey. Okay. And let's see. Did I call it tile frequencies? Did I just spend all that time saying tile frequencies? Frequency hints. Frequency hints, frequency hints. Okay. Alright, there we go. so for this particular tile, we need to, with the hints, get the total times. Oh, and the cell's possible patterns. The cell's possible patterns. If that cell is possible, then we add it to the total. Okay. We add its relative frequency. Okay. So I'm going to call frequency. Call that relative frequency. I could have done that faster, but got multiple things going on at once up here. Okay, let's jump back down here. So frequency hints. Okay. We're gonna fold. Function. Start with 0. Over cell possibilities. And this function is to be int bool int. Some possible cell. Okay, so some possible cell, that's our count, our accumulator. Total. And if it's true, do something. If it's false, we just have to return total. We just ignore everything. So what can we do in the true case here? Well, we have to get a number somewhere to add to total. Return an int. That thing we're going to get, though, is going to be from frequency hints. So what we actually need in cell possibilities is the association list, I think. I'm going to change the type of some possible cell a little bit. This will be pattern indexed blue. And in the false case, we don't care about it. And there's our other number that we need. Total shadows. Oh. Call it. Count, then. Something like that. There we go. Okay, so our total possible tile frequency. Let's see. Yeah, I think that's about right. And then we can do the sums. We have the total weight from total possible tile frequency for that cell. And then we sum of weight log weight. So I think this is where we add up all of those terms, or at least in the simplified version. Beep, beep, those ones. Yeah, so there's the terms. Times log 2, or 0, and then sum them together. And then we return the total weight minus those divided by the total weight, which lines up to that, corresponds to that. That's pretty good. I like that. Nice and straightforward. Okay. And so we call this entropy. This is the entropy function. This is the main one. We take a cell. We need the frequency hints. And we're going to turn a float. A double. Maybe a float. Maybe double. So we get the cell, we get the frequency hints. Let's go. That. Boom. We're going to start off with a let binding of the total weight, which is the total possible tile frequency for that cell. Given the frequency hints we have. And we also need the sum of weight log weight. And then we're just going to go through the possibilities for this cell, mapping it to some floats, and we're going to sum them together. We're going to take the array association list of the cell possibilities. There we go. Sorry, like that. Okay. So this hole here is our main kind of function. We'll call it to log. To log weight. Makes sense. Where to log weight is going to be a list of pattern indexes with their values, and we return float. We need to add a map in there. Oh, what's the problem here? That. What's this one? Bool with int. Oh, sorry, my bad. There we go. Alright, cool. 6 is possible. Okay. So in case it's true, it's possible. X false. And that's kind of the split we want. In the case where it's true, we know we can do this formula here. We take the relative frequency for that tile that we're mapping over, and we multiply it with its log 2. So we get its relative frequency. Relative frequency of this tile index in our frequency hints. And we RF times 2 of RF. I don't know what our log2 function actually is in Haskell. Do we have one? Well, let's check. Is there one in base? There's one in kryptonite, math functions. Is it called something else? That wouldn't be called that. Weird. Let's Google. It's called log base. That might be our one. Okay, log base. Although, how do we get the log base of our floats? No, we could just do 2.0. Yeah. Log base. Oh, maybe int, yeah, because relative frequency might not be in there. Well, now we have a design decision to make. Because the frequency hints is ultimately a map underneath, it means that if we try to look up an index in it, a pattern index, even though at this point when we're calling entropy, we kind of sort of already know that it's going to be in there. But Haskell doesn't let us kind of like take shortcuts like that, so we'd have to blow up or return a value. Okay. This code imp function always returns an F32, even though we get a reference to these frequency hits. And relative frequency also returns a size. So I guess they could get around this by returning 0 if it's missing. Which would be kind of the same as saying it's not in there. And so this would return 0. And be the same as the empty case. Yeah. That's probably the better way of doing things. Let's go with it. Relative frequency. Let's go off of maybe int. We'll do maybe 0. For IB. Cool. And now this is the problem with this is couldn't manage expected type float with actual type int. Okay, so our relative frequency we have to explicitly cast up to double our float from our integer relative frequency. I think that takes care of that. And then, so this empty case here, they just return 0. Okay, so then we have one little hole to fill in. We got the sum of weight log weight. Then we can do our final total weight minus this. We take log base. I'm going to turn that into a helper function, but I'm just going to write it out this way for now. 2.0 total weight minus the sum of weight log weight divided by total weight. Wants a float? Yes, it does. Not a problem. Okay. There we go. Okay, specs are broken because we changed a couple of types. Yeah, we'll fix those up. But this is looking good. Okay, so we got our entropy calculation. Okay, I'm kind of just looking at the implementation for that because, you know, it's a bunch of stuff. But of course, this is going to like calculate a bunch of stuff. So caching, because we're going to be recalculating entropy as we go along in our algorithm, right? When we choose a cell with the lowest entropy, we collapse it. And then we propagate. And so when we propagate that choice out, right, we change the amount of cards in the stack, to use my previous metaphor, or visualization. Visual metaphor. Visual for. Anyways, we collapse out that stack, and so that cell's state has changed, and therefore the entropy of that cell has changed. And so we need to recalculate that entropy. As you can imagine. Recalculating all of this for every single cell on all those propagations. Gonna get expensive. And there are, it turns out, based on this blog post, there are parts of it that don't change a whole lot. And so we can cache those parts. Alright, so it can be made constant time with caching. Throughout the course of this algorithm, possible tiles will be removed from cells. The only time a cell's entropy changes is when a possible tile is actually removed. Alright, so the caching strategy will be able to keep a running total of the sum of the possible tiles, so that weight, and the sum of weight log weight parts. Alright, so this caching strategy will basically compute these values, I guess, in our entropy calculation and stash those in the cell and in the cell data. And that way we just compute it when the cell's state changes. Saving us a lot of work, which I think is pretty smart. Okay, so let's implement the caching, and then we'll go back and get the test working again, just kind of clean up what we've done, and then we'll see where we're at from there. So I'm going to go ahead, since this actually works and compiles, but we haven't written any proofs that it works, but or any kind of examples to at least demonstrate and convince ourselves that it works, but I'm going to say it works. I'm just going to commit that there. Maybe we will write some tests for it just to make sure we know we have a good sense of these things. Okay. Add entropy. Okay, and let's add caching. So we go cell total weight. Okay. Don't know what that should be there yet. And cell sum of weight log weight. Like that. Float. Also a float. And there we go there. Did I spell it right? Total. Oh, I called it sum here. Yeah, of course. I'm looking at the wrong part of the word. Because I called it sum of weight log weight down there. What's we're gonna do? Sum. Okay. Okay, so we've got to put something in here for the holes. Sum of. So I guess we got to calculate these out and that out as well. We could rip these into functions. Yeah, I think so. We'll put them here. All right, that's going to be cell total weight. What is it going to take an input? Frequency hints. A cell. And return a float. Maybe it'll be a little awkward using our initializer. No. It'll be fine. We won't be able to do it there, but there's a way to do it. So yeah, let's just finish this here. Cell hints. And we'll just pull this up here. And put it here. And then we can cell total weight. Cell and hints. And the problem with this is multiple descriptions. Oh, I named this. Yeah, what's called total weight then. So internally here. Call this one PW. Take those two and call them TW as well. I should take care of that. Yep. Okay. And we'll move sum of weight log weight. That all, what does that need? It needs 2 log weight. It needs the cell. And weight log weight needs the frequency hints. So, cell, frequency hints. Weight log weight. Hints. And pop that bad boy there. Put that there. That. There. Put that there. We're good here. Let's just clean this up a little bit. Okay. Now. Alright. And then, so up here, we can initialize this with... But we're going to need the frequency hints in order to construct the cell. I'm looking for their what I was going to do is like initialize that to 0, but then I have to pass in the frequency hints in order to construct the cell. So I'm just looking how they took a similar tack as well. Okay, they initialize it here. Cell template, core cell. Possible vectors. Here. Well, they sum it up right there. And they take the function there, which means they have the frequency hints and scope when they call this. Up there, yeah. So we would have to pass it into our make cell here. If we have the pattern result, we can actually calculate the frequency map. Well, we don't actually want to calculate the frequency map when we call make cell. Ooh. Make cell's probably gonna be an internal implementation detail, so I'll make it a parameter. Frequency hints here. So we initialize it to 0, we let bind the initial cell. Do it that way, or... So basically we would take cell and then we would apply C such that cell total weight equals total weight. C with hints. And cell sum of weight log weight is total sum of weight log weight sequence. Right, we could do it like that. Or if we just take the cell possibilities as an argument, because that's all we're really using cell for in sum of log weight and, well, total possible tile frequency. Well, it's also using that. Basically, if we remove the cell requirement, then we can just pop those in the arguments here in the constructor, and we don't have to do this let binding with this. So we just pass in all possibilities. Let's try that. I'm going to stage this. Add cached cell weights. And let's just try refactoring that out. Being that way. See if that works. So instead of this, all possibilities is going to be an array, a pattern index to Boolean. Or pattern index to Boolean. This thing. Possibilities, and then we just call possibilities here, and everything else is the same. Total weight, array, pattern index, bool here, possibilities. I'm using the same word for the argument, so I might as well probably make a type wrapper for it, perhaps. Possibilities, and sum of weight log weight. Okay, and a couple of type errors. Yeah, okay. So I should be able to get rid of that. Go back to here. And then we can do total weight, all possibilities. We still need to pass the hints in. And then sum of weight log weight, all possibilities, and hints. Okay, and now, we got to clean up entropy now. Which is fine. Alright, the simplified version of it now can just entropy, yeah. So then we can just simplify the expression down here. Right, so we can get the TW and sum of weight log weight out of the cell. We don't use cell anywhere else for that. So I think we can just pull it out with the overloaded records. That. Okay, and then our make grid just has to be updated here. Because we pass in the histogram to it, or the frequency hints. We could calculate that up here. The pattern result. Hints. Yeah. And to calculate the frequency hints, we have to use the frequency hints function, the list of pattern A's. So the pattern result. Patterns. Pattern result patterns. Yes, that's the one. Word E. It's probably demanded by frequency hints. Okay. Then entropy just needs the cell. Yeah, it doesn't need the hints anymore. Okay. X here. Okay. Yeah, okay, cool. All right. What else? Yeah, that's a function. That should just be hints. Oh, we're not using hints in total possible tile frequency here. Which is kind of a hint that either we don't actually need it, we should remove it, or we didn't implement this properly. Total possible tile frequency. We have to look up the relative frequency for a given tile index if it's possible to add it to the sum. Which we get from... They're looking it up in frequency hints. For the tile index in the possible tiles. Okay, yeah, so I think we do have to use it. We don't add the X here. This is the X we want to look up in that hints map. So, relative frequency. X and hints. There we go. Of those in the test suite, but otherwise we're good. Sweet. Okay. So now we just need to add the a couple more cell functions for removing a cell from the set of possibilities, or removing a pattern from the set of possibilities, which will have to update our cached entropy calculations. And all that stuff. And all that. So let me, do we have a to-do file here? So I remember this for next week. Go. Let's start one. So we need to remove possibility. Tile index, or pattern index from the cell possibilities. And update cached entropy values. Cool. All right, let's check this in. Cached values. Okay. And we'll quickly fix the spec, and I think we're running low on time for the rest of the stream, so we'll just go quickly fix the spec, and then I think we'll call it there. So we'll go to the test directory, go to spec, and our failing ones. Yeah, the frequency hints test, no problem. It's just going to be some unwrapping, I think. Alright, so generate frequency hints. It returns a frequency hint. So this should just be composed with another function here to get those out from the new type wrapper. What we called get frequency hints. I should leave just the one, I think. Pattern result. We want a pattern result of frequency hints, not a list of patterns. And so that'll be pattern result patterns. And then one more test to fix. 15. Yeah, so length of patterns. Just want to compose that with pattern result patterns. Cool, we're back to good. Wait. Okay, cool. So let's take a look at our work so far. How to cells and grid, entropy functions. We could probably make sense to squish this down. Maybe it might make sense to squish this down to one big commit. Let's see. Pattern results, subpatterns. Create cell, make cell collapsed in grid. Then we added entropy stuff, cached cell weights and the values, and then we fixed the tests. The test fixes are because of changes to pattern results and frequency hints. Yeah, so that test one kind of depends on these two. This one and this one. Yeah, so I don't think there's a way we can order these to structured in two. I'll just, yeah, I'll just squish down to one. Word that. Good. Right. Grid is initialized with all with patterns extracted from preprocessing. It contains cells that have all the possible pattern indices at first. Also added the entropy function for determining which cell to collapse next in the algorithm. Super duper. I'm gonna just get rid of that. Up. That's good. All right, pushing that up. So if this is your first time tuning in and you like what you saw, thanks for watching. It was nice having you. I'm always open to questions and diversions, by the way. So backseat programming is all fine, or if you want to talk about your projects or anything you get stuck on, also fine too. I do these streams basically once a week on Tuesday evenings, 10 after 8 in the evening or so, in the Eastern Standard Time Zone. So if you want to just write that down somewhere and follow it, set yourself a reminder, all good. If you want to get notifications from Twitch, then just give us a follow and set up your notifications, and you'll get notified when I go online. Which does happen sometimes outside of my normal schedule once in a while. So you'll get those. If you are just following my video on demands on my YouTube channel, then you know what to do there. You can subscribe and like, and helps everything out. Gets more visibility for the stream, for Haskell in general, and things like that. So you can also follow me on the Fediverse. I'm on the TypeStop.pl server in Mastodon there. So give us a follow there. My profile also has all of the links to all my stuff. So like my Twitch stream, my YouTube channel, my website as well. And what else? We also have a Discord server and a Discord channel on a Discord server, actually. So if you go to the link above my head, that's declarative.tv. It's a cool little website. It's got a link to a Discord server there. There's a channel for this stream. So if you didn't get to ask any of the questions you wanted to ask on stream, or again, you're in a different time zone and you're following along, then give us a chat there and ask questions there and talk about your stuff there. That's pretty much all I got. So thanks for tuning in again. It's been wonderful, and I'll see you next week. May your monads always be free and your types always check, and have a great time hacking out there. Take it easy.